So welcome to this last session. So this session is about threading. It's an advanced topic, so I expect we're going to go technical here. So I expect you know already a bit or even a lot about Qt and threads and stuff. So before we start, let me introduce myself. I'm from Belgium, near Liège. So I speak French, in case you wonder. While I was a student, I was helping KDE. Do you know KDE? Have you heard about it? Good. So after developing KDE, that led me to join Trolltech as a developer on Qt, which later was acquired by Nokia, as you know, still as a developer on Qt. So within Nokia, I was working in many areas of Qt. So I did a little bit of everything. So I was maintaining Qstyle, the item view framework. I helped to port QtScript to GSC and then to V8. I worked on the QML debugger that you can find in Qt Creator. And so I rewrote some of the internals of QObject, the signals and slots, the way they work. So I'm a generalist. I like to touch a little bit of everything, including threading, of course. But recently I left Nokia, and some months ago I just created a company with another colleague, and we offer Qt services. So that was about me. So now let's talk about the threads. What is a thread? So I was wondering, so I took the dictionary and looked it up, and apparently that is what it is. But that's not what I'm going to talk about, obviously. I'm going to talk about multiple threads. So in this presentation, my goal is to review how the threading works in Qt. But the main part of this presentation will be an introduction to log-free programming. I don't know if you've ever heard about what log-free programming is. Who here know about it? Some hand, and that's perfect that it's so few, because I really want to introduce you to the concept and to open your mind to the concept of log-free programming. That's the goal of this presentation. And then we will use this concept I try to explain a bit of the internals of QMutex and Qt 5. So let's start. When to use threads? So there is good reason to use threads and bad reasons to use threads. Good reason to use thread is to keep a user interface fluid and responsive. If you have one blocking operation that takes a lot of CPU, and that runs in the threads that are also supposed to update the interface, then the interface will block and the user will notice, and that's bad. The other good reason is to parallelize expensive operation. You know that those days the computers get more and more CPUs because it's harder and harder to make the CPUs fast, so we'll just make more of them. But then we need to use threads to benefit of all those cores. So Qt provides a lot of classes to do threading, some low level, such as Qthread, QMutex, and so on. Who of you have already programmed with threads with Qt? Perfect, a lot of hands. So I don't need to explain all of that. I expect you to be familiar with the basic concepts, at least. And then some more high-level APIs, such as Qt Concurrent, QFuture, QFuture Watcher. I'll show a quick demo how to use Qt Concurrent. And then some class that maybe are a little bit less known, QAtomicInt, QAtomicPointer. I'm going to talk more about those classes later. But first, let's do a small demo. So I wrote a QML application. This is it. Oops. So yes, QML is. I was told that QML is nice to do great UI. That everyone could do beautiful stuff, so I tried, and that's what I got. So it's good for designer, I was told. So I wanted to compute Fibonacci number. Why not? So here I enter the number, and so the third Fibonacci number is 3. The 4, 5, 8 is 34. So you know what the Fibonacci number are. The series, it's all every movie about mathematics. And yeah, I can also compute high number, but the problem is that my routine to compute the Fibonacci number is quite slow. So while I compute the number, it blocks the UI. And I want to fix this issue. So my QML is quite simple. Remove all the unnecessary thing. So I just have this text that you saw. It was turning, so I made an animation to make it turn. And the text is the fib property of a Fibo object. That is an object that comes from the C++ side. And if this number is 0, then I show the text loading. Else, I show the number itself. Then I have a text input, and this text is the button, which once pressed, I ask to call the compute fib function from the Fibo object with the number that is entered in the text. And then the C++ is quite simple, so I create a fib object, which I expose as a Fibo object. And this fib object has a fib property, which is the one that is displayed. And I have the function compute fib, which will call the function fib here that computes the Fibonacci number. And you might say there is better ways to compute the Fibonacci number, but for this example, I just wanted something very slow. So there it is, as you learn it at school. What I'm going to do now is instead of computing directly the Fibonacci number here, I'm going to set it to 0, so it will show loading. And then I'm going to use Qt concurrent, run, and I will run the fib function with the parameter f. And then what do I do with that? What this function does is that it will run the function in a thread. But I would like to get the result of this function, and I can get this into a future, which I will store here. If at any case there is any question, just raise your hand and ask. Future. So I create my future. But I also want, so this future basically contains a reference to the return value that is not computed yet, because it's going to be computed in the thread. What I need to have now is to get notified in some way that the results are available. So I will just create a signal, a slot. Just call it callback. And this callback will do set fib on this object of the future.result. And when will this callback be called? In order to get the callback called, I need another object, a QFutureWatcher. And this QFutureWatcher, I will connect the signal finished. I will connect the signal finished of this watcher to the new slot I just made, so the callback. And I just need to say that my watcher is associated to the future that I just created. And there it is. Let's try that. So I still compute the number, and if I enter a big number this time, we can see it's load and the animation continue to work. Is there any question on this? Yes, there's a question there.
Are you limited to what you can do in Qt concurrent run for things that don't actually need to have any other interaction? So something that will run to completion without error. So in the case like you're calling fib, you know that that's going to run, you can guarantee that it will exit.
Okay, so
so are you limited to calling functions like that where you know that you guarantee that they finish, rather than things that may...
So functions that have an infinite loop inside.
Yeah, or anything that might stop for user input.
So in that case, you want to abort, for example, you compute the number 300, and that might take hours, and you want to abort it. So yeah, this Qt concurrent by itself would not let you do that. So if you would do that, you could have, for example, I'm quickly writing code there, so I'm not going to run it. It's pseudocode. So then you will have a mutex and a bool property like finished, and then you will under a mutex and so lock my mutex, and if finished, return -1, for example, to indicate a failure, and then the abort operation will set this finished flag. So if it was in a loop, you would put that in a loop, or maybe every 10 iteration, every 100 iteration, or in enough case in order to abort the operation.
Thank you.
Yeah, yes. So that answers your question. Yeah. Okay, good. Any other questions? Yes.
Is it possible that fib function is a member function of the fib class?
Yes.
Can you demonstrate that, please?
Yes. So remove this. So you make it just a member function. I mean, if it was static, it will be really easy because you could just take the address. But in that case, it's a member function. So you use the name. It's fib. So you can use. I think so. So it's a pointer to a member function, and then I think you need to pass. You need to pass the class first, so you do something like that, which I think will run. Let's try it. Yes, it compiles. Any other questions? Then. So that was the demo. So let's start with the other topic, an introduction to log-free programming. So log-free programming means basically programmation without mutexes. So why would you want to do that? Why would you want to get some algorithms that works without locking? What's wrong with mutexes? Often they work. Like I used it in the sample, a very simple example to check finished. Mutex are just, they're perfectly fine, so use them. But there are still some disadvantages of mutexes. One of them is that if one thread lock a mutex and then go to sleep for any reason, like he lost his time. It's so the operating system just scheduled the task down because there is a page fault or anything. And then all the other threads that want to acquire the same mutex are going to also need to be put in sleep, waiting for the other thread which is put in sleep. So you get more context switches, which waste CPU time, which you would like to use for your computation rather than for the context switches. And then, is there anyone here doing real-time application? Very few. That's to be expected if you do UI. But in real-time application, there is some cases like your threads have different priority. And if a thread that has a low priority locks the mutex, the threads that have a higher priority need to wait for this thread with low priority. Threads are unsafe because you can get deadlock if one of the threads is killed while holding a mutex. Then you're in a bad situation. And convoying is also means that all the threads need to wait for the slower threads that holds the mutex. So that's why some people do log-free algorithms, because they're usually faster, because there's less CPU wasted in the logs, and no risk of deadlock. But there is bad side. It's like threading is already known to be very hard. I don't know why, but if you try to make it log-free, it's even more difficult. So to me, it's also more fun, which is why I want to introduce you to this concept. First, I will just show you explain you the QAtomic API. Then we will go with an example, the log-free stack. And then we will analyze a small problem, the ABA problem. So we have two classes in Qt, QAtomic int and QAtomic pointer. Each of those classes holds the primitive. So for example, QAtomic int holds an integer, and you've guessed it, QAtomic pointer holds a pointer. And they have very similar API. So they have this set of functions. You can test and set, fetch and store, fetch and add. And each of those functions, you need to explicitly pass the memory ordering. I'll talk about the memory ordering later. And so you mix and match to get the API, like here, test and set acquire, or fetch and add ordered. So for example, here is fetch and store. This is not how it's implemented, but this is what it does. So what it does, it returns the old value of the pointer in that case, and sets the new one. So it basically exchanges the value. But it does it in an atomic way, which means that at any time, the memory will be consistent. The memory will be either the new value. After the operation, the memory will always be the new value, and it will always return the previous value, while knowing there is no other value that has been set before by another thread. So this is really implemented using assembly in Qt. So there is it's one of the very few, very small part of Qt that contains assembly, and that is so platform specific. Is really those atomic operation. Fetch and add is just the equivalent of plus equal, but in an atomic way. So you have, so you know that if you do plus plus, if you increment something in two threads, that might be wrong. Like you can have intermediate value, or you add to the previous value rather than to the new value. And then the most interesting one is test and set. It's also called compare and swap if you read the literature about it. So this will change the value to a new value only if it is an expected value. And if another thread has changed the value in the meantime, it will just return false. And else, if it's the right value, then it will return true. And then the memory ordering. So you might be aware that current CPU have what is called out-of-order execution, meaning that at each clock cycle, the CPU will fetch some instruction from the memory, like 6. We'll put everything into some register. We'll analyze the instruction, and there is some wire within the CPU that will try to compute the dependencies between those instructions. And then they will be executed in some order in order to keep the program running as if it was in sequence, but seen from one thread, which means that other thread might see the program is running in a different order. And we want to avoid that when we do atomic operation. We want to be sure that the stores are not reordered in a way that will we want to be sure that the operations are not ordered in a way that will not leave the memory in a consistent state. So we have the relaxed memory ordering. That's the one that says that this operation there is no memory barrier. It's just like if all the operation can be reordered before or after. And there is the ordered one that says no operation can be ordered before or after. And then there is the acquire, which means that every operation that is done after needs to be done after, and every operation and release is the opposite way. Every operation that is done before needs to be done before the atomic operation. Is there any question on this API? QAtomicInt also has some convenience API, which are ref and deref, which is basically plus plus or minus minus. So let's start to use this API in the log-free stacks. So I made some nice graphics to draw there a stack. So you have a pointer to the first node, and each node has a pointer to the next node. It's basically a linked list. You should be familiar with that. So when we want to push, so in that case, we want to push the node C. So we say that C next equals B, the current head. And then we will atomically change the head from B to C. We pushed. That should not be too difficult. The problem arises if there is two threads and both wants to push one node. So both of the threads sets the node next to the current head, which is B. And then we'll try the atomic operation, the compare and swap from B to D. And in that case, the thread 2 goes first for any reason, and then D is pushed. And what will happen is that the thread 1, the atomic operation will fail. So C is not pushed. And the thread 1 is notified that the operation has failed, so it can start over. And this time use D as the next node for C. The pop is really similar. We just here want to pop B, so we will change head atomically from B to B.next, which is A. So we can pop B. So that's how it works. Let's do it. So I have a program here that this program will push a lot of nodes to my stack, and then we'll pop all those nodes. So here I implemented I re-implemented QThread, and I have a run function that will push a lot of nodes. So it allocates a node and push it. And then I have another function that inherits from QThread that will pop all the nodes and up to when the stack is empty, so when node is 0, and will count the number of nodes that has been popped by thread. So the first step, I have a timer. I have numthread here is 2 because I have 2 cores on this computer. So I will start 2 threads, 2 pusher threads that are going to push a lot of nodes, wait for them to finish, and compute the time it needs to pop all those nodes. And here counting the time it takes to push all those nodes, and then the same thing with pop. I will compute the total number of nodes that has been. So I will create 2 threads that will pop all the nodes, wait for them to finish, and compute the time they took to pop all the nodes. You can see it in action. So it took 900 milliseconds to push all the nodes and 700 milliseconds to pop them all. But in this stack, it was implemented using a mutex. So this is how you would implement a stack in a normal mutex way of doing. So this one is perfectly fine and fast enough, I suppose. But let's see how we can do it without having the mutex. And instead of having a pointer to the node, we'll go to have a QAtomic pointer to the node. And then we don't need the mutex locker. And we'll do in a loop. We'll do this. But so we'll loop until this, and we want to do this in an atomic way. So the previous value was n.next, which we saved at the line before, and so we expect n.next, and we want to exchange it to n. That's for the push. And the pop, that's very similar. So if the node is null, that means the list is empty. And we expect n, and we want to change with n next. That's it. Any question on the implementation that we're going to try here? Hopefully it works. And it worked, and as you see, it's a bit faster. So why is it faster? Because we are now in a log-free list, and the more you have core, the more I expect it to be faster, and this is only with 2 cores. And you see that we go from 700 milliseconds to 400 milliseconds to pop, and from 900 milliseconds to 600 milliseconds to push. Is there any question on the log-free list? Yes, there's a question there.
Is this really log-free? I mean, the atomic functions also must have some implicit log so that other cores cannot change the data.
This is lock-free. So as I said, it's implemented using some assembly, and there is assembly. So there is an assembly instruction in the Intel computer, which is called compare exchange, which is going to do exactly that. So it will do the test and set, and it's one CPU cycle, and indeed it will fail it will do exactly that. So it will either succeed or fail. So it's atomic, and it's only one instruction without lock. So it's also a slow instruction because internally I don't know much about how CPU works, but it needs to check that the cache line is not shared amongst CPU, and if it is, it's like as slow as a cache miss, L1 miss. But it's still much faster than a lock.
Yeah, but it's also kind of log, right? I mean, if the other core wants to change exact the same register, then or the same.
No, it's not. It's not lock, because if the other CPU will change the same register, then the operation will fail.
Okay, and it will repeat then.
And then it will repeat, and we will have this loop there.
Exactly. Okay, then this is the kind of log. Okay.
Yes.
Okay, thanks. I understood.
No more questions? So then we will see what the problem with this implementation is, because there is one. So in my little program, it works because I push all the nodes, and then I pop them, and I don't do both in the same time. But in a proper lock-free stack, you would like some threads to push and some other to pop. Let's see what happens if thread 1 wants to pop the node A. But so then it says it tries to replace head from A to B and return A. But just before the atomic operation, the thread 1 is put in sleep mode, and the thread 2 do some work. So the thread 2 will pop the node A, and if thread 1 wakes up at this point and try to do the atomic operation, the atomic operation will fail, so there is no problem. So it will try again, try to pop B. But thread 2 continues and push a node. It pushes the node C. So what would be the problem now if thread 1 wakes up? Well, the atomic operation would fail, so that will not be a problem because we will try again and pop C. But unfortunately, thread 1 still do not wake up, and thread 2 continues, and thread 2 pushes A back. You can do that. And now, what is the problem if thread 1 wakes up? Well, the problem is that the atomic operation succeeds because head is A, as thread 1 expects, and then we'll change the pointer from A to B. And the problem is the node C. The thread 2 thinks it pushed, but now it's leaking. So we have the problem. It's called ABA because we have A, then we change it to B, and then back to A. And it could be worse. It could be that the thread 2 pop A, and then pop B, and then pushed A back, and then head still will point to B, which is supposed to be popped. So we have this problem. So how will we solve it? Because there is, of course, a solution to this problem. So one of the solutions is to add a serial number with the pointer. So you can make sure that the nodes in that case are properly aligned, so you have enough bytes at the end of enough bits at the end of your pointer that are 0, which you can use to add a serial number that you increment every time you push something to the stack. which means that if it's A again, the serial number would have changed. Some architecture have multiple word compare and swap, and you can also implement multiple word compare and swap using a normal compare and swap. There is some paper on the internet how to do that. There is also some paper on the internet talking about the hazard pointer. It's a concept in which each thread has a list that is seen by the other thread that tells the pointer that the thread is about to access, so those pointers are not released into the stack. And then some architecture like PowerPC has this instruction set load linked store conditional, which at the point you load, you mark with a flag the address, and when you store, it will only store if the address has not changed. But this is not very common in many CPUs, and you're also very limited in the operation you can do between the load linked and the store conditional. Is there any question about the ABA problem? Or about this log-free programming in general? So if there is no question, let's apply again what we've seen and try to explain how QMutex in Qt 5 will be working. So yeah, QMutex in 4.7 applies already some of those similar principles, but in Qt 5, we would like QMutex to be a POD without any constructor. And the reason we want to do that is because if you have, like when I had the question in the previous example, I added a QMutex as a global data in my file. And those are global objects, and QMutex has a constructor, and there is a policy in Qt which says no global object in the library. And one of the reasons of that is that there's many problems with global objects, such as you don't know in which order they're going to be initialized, and you're going to call the constructor of those objects when the library is loaded. And even if it's in some, because Qt is big, and there's many parts you don't use in a library, and even if you don't use this part of the library, you're going to pay the cost of the initialization of all those global data. So we try to avoid global data. That's why if you've read the source code, there is the global objects are inside the Q global static macro. But this also has a cost, so having it as a POD is perfect. Also, QMutex is now just a pointer, which means that it's really cheap. It's only 8 bytes on a 64-bit machine. It's just the size of a pointer, and there is no hidden allocation. While in Qt 4, you have hidden allocation behind each QMutex, because each QMutex has behind the scene, you don't see it. It's not part of the API, but each QMutex has its own QMutex private that needs to be initialized. That is 100 bytes maybe, and that also initializes some platform-specific data structure to contain the mutex. But in Qt 5, what we've tried to do is to have QMutex, it's just an atomic pointer to the QMutex private. And this is not always a pointer in the sense that there is two special values here. So if d is 0, which is how it's initialized, if d is 0, then it means the mutex is unlocked. And the other special value is if d is 1, which means the mutex is locked, but there is no other thread waiting of the mutex. So the only thread, so the mutex is locked, but no one is waiting. And then all the other values are a QMutex private, like some internal stuff. So then that makes locking and unlocking very simple. If you don't have any contention, so for example, if you use a mutex in a library, you don't know whether or not your users will use threads, so you're forced to use QMutex. So what's the price here? It's just a test and set acquire from 0 to 1. So if D was 0, which means unlocked, and you can switch it to 1, which means locked, so you just lock the mutex, you're finished. If this operation succeeds, you can return true, try lock has worked. If it returns false, it means it didn't work, and we're going to see later how we need to lock it. But so locking is very simple. And unlock is the same. So we're going to change the value. So if we can, so yeah, when we unlock, we always reset the value to 0. If it was 1, if the old value was 1, it means there is nothing to do because no one was waiting. If it was not 1, it must be a pointer. It cannot be 0 because you cannot unlock a mutex which is not locked. So if it was not 1, it's a pointer to a QMutex private, and then we'll use the wake function, which is some platform-specific code to wake all the waiting threads that are waiting on this mutex. I said here simplified because that's not in Qt 5 we don't want to wake all the waiting threads here. So this implementation I'm going to show you is a bit simplified because I want the talk to hold in 1 hour. But yeah, let's continue. And then you see this dref here, which means that the QMutex private is ref counted. So let's see how QMutex private looks. So we have this ref count, and so let's look at the ref. So if the ref count goes to 0, we want to release the mutex private. So there is something very special here, is that we never can delete the mutex private. Because if we delete, the code that is going to try to lock will read the value of D, will see, oh, it's a pointer to a mutex, I'm going to ref it. But what if in the meantime, so from the time we read the address of the pointer to the mutex private and the time we ref, what if the mutex has been unlocked already and the mutex private freed? So we don't want to access freed memory. So we're going to release here, and release will just push this mutex private into a pool of mutex private, and it's a lock-free stack as I've shown, but yeah, basically it's a lock-free stack with protection against the ABA problem. And the ref is also a bit special, so it's not just an increment, but it's an increment which checks that the ref count is not already 0, because I don't want to increment the mutex private if I was equal to 0. So the ref will return false if the count was 0, or will return true if the ref count was incremented. So we have release and allocate that are just going to push or pop the mutex private from this lock-free stack. And yeah, allocate will also make sure that it's properly initialized, which means that it's not in a wake state, because the mutex private can also be in a wake state. So we have those two platform-specific functions here, wait and wake. And once wake is called, every call to wait will return immediately. And so while wait will be blocking and wait for for the thread to call wake. So internally, it's basically implemented with a wait condition here. But I don't want to enter into those platform-specific details. And we're going to analyze the code of lock, which looks like this. So first, we try to change the mutex private from 0 to 1. So it's basically the try lock as we've seen before. If this works, so if it returns true, so this condition will be false. So if it works, then there's nothing to do. We just return. So if we change from 0 to 1, perfect. But if it didn't work, then we're going to take a local copy. We are going to read the value of D. The value might have changed between this test and set. So it might have become 0. So if it's 0, it means it's unlocked. So we continue. We start over. We try again the test and set. If it's equal to 1, then we need to allocate a new QMutex private and set it instead. So that's what we do. We allocate the new mutex private, and we try to set it. But it's very possible that in the meantime, again, another thread waits for this mutex private, or the thread has been unlocked. So if this operation fails, if it was not 1, copy here must be 1. If it was not 1, then again, we release the mutex private if needed, and we continue, we start over. We again try to change from 0 to 1, and we go. Else, we're going to use this new mutex private as our copy here. We'll try to ref it. Again, as I said, it's very possible that this mutex private has been released and then used again in another mutex. So if it's been released, and so we try to ref it, and the reference count is 0, it means that the mutex has been unlocked, which means we can, again, start over, try to test and set from 0 to 1. And if we also need to check, once we've refed, that we have refed the correct mutex. Because as I said, our mutex private could have been reused in another mutex. So we need to check that D is still copy once we have referenced it. We are sure that from the point we have called ref, it's not going to be reused in another mutex, but it can have been reused in another mutex between the test and set and the time we ref. And then, once we've done this comparison, that we're sure that we have a pointer to the right mutex private, then we can call the platform-specific code to wait. Is there any questions? No questions. There is a question.
Did you make some tests? How long it will take if you have a while there? Maybe you enter an endless loop and have a core with 100% waiting to lock unlock. How you avoid this?
So we have some benchmark, and in practice, this do not happen. So how can I tell that? But let me think of an answer. Well, in practice, this do not happen because each operation will try to each operation here is really trying to advance something. So if it fails, it's because another thread has done a lot of work. It has locked and unlocked the mutex behind. So it's not going to use 100% of the CPU because that will mean that one of the thread is really slower than the other thread that can lock and unlock and lock and unlock on this part of the code, which is quite unlikely. Could happen, but not not if the thread is not put into sleep, which means that if it fails, it's because the thread has been put into sleep, which means it doesn't happen.
Okay.
Any other questions? Or is everyone lost? Or is it crystal clear for everyone? So this, as I said, was a simplified implementation. It's a so the implementation that I just shown you here has some problem. One of the problem is that we wake all the threads that are waiting for the mutex. Then all the threads are going to be waken up and will try to acquire the mutex again, but of course only one will win the race. So there is no point waking up all the threads. We only want to wake one thread. The other problem is that it doesn't work with QMutex try-lock if you pass a timeout. So that's why the real implementation is a bit more complicated. So on Linux, so all of what I've shown here is on all platforms but Linux. Because on Linux we use mutexes, so it's basically exactly the same principle but implemented in the kernel directly. So QMutex on Linux is also just a pointer to QMutex private, which is either 0, 1, or some data for the mutexes. We support recursive mutex, even if those always have a QMutex private. We support try-lock with a timeout, and all of this needs the implementation to be a bit more complicated, even more complicated. But it works. So that's it for my talk. Is there any questions? Yep.
So can you give us a small rule of thumbs how to use QThread? When I ask this, I refer to documentation which says use QThread with subclassing. Mm-hmm. Although in Nokia blog we can see also some other recommendations like aggregation or composition. The first question, that was the first question, and the second question is when to use QConcurrent and when to use QThread.
Okay, so yes, I've used QThread in my log-free stack implementation, and one of the reasons I use QThread is because it's very simple here, and I also want to have control of the number of threads because I did some benchmark using more or less threads, and I really want that. But in practice, you don't want to write benchmark. You want to write code that do stuff, and you have other mechanisms in Qt like the signal slots that are thread safe. So you can emit a signal in one thread and receive it in another thread. And in that case, it's better not to subclass QThread, but just call QThread exec, which will run its event loop and then use the event loop of the Qt event loop with the signals and slot mechanism, the event handling between threads. So in my example, I don't use the event loop of the threads. I write my own loop. It's not an event loop. So that's why I subclassed QThreads. But if you want to use Qt event loop within the threads, then you don't need to subclass QThread. And then regarding when to use Qt concurrent or when to use a low level like QThread, I think you should try to use Qt concurrent. It simplifies things. So if you have one operation, there is no magic answer there.
So you're saying we can treat them equally, or we can just say QConcurrent together with the QFuture and QFuture Watcher can bring us some benefits in this use case, for example, when we communicate between threads via signal slots.
Mm-hmm. Yes, if you really have something to do in a thread, then use concurrent. Like for if you do some CPU intensive operation and say I want to do something in a different thread, or I have this map of a lot of, or this list of a lot of things, and I would like to do it for each of those elements, then use concurrent. But if it's only for passing information from one thread to the other, then you can, or if you want to have an event loop in one thread, then you need to use this. You cannot use Qt concurrent if you need an event loop in a thread.
Okay, thanks.
I have a question regarding thread pools.
Yes.
The mutex is used inside the QRunnable are affecting the real thread. And you will also use the same functionality also inside thread pools. I mean the thread pool manager, or how I could call the object which give me the thread from the pool which is active.
Yes, exactly. So what is the question?
My fear is that that mutex, okay, if I take only one thread which I control, no problem. But if I use a thread pool which might have 100, 200 threads, I may get into troubles with this kind of atomic operations, because I have a lot of operations in the same time, trying to write, to read in the same variable.
Yes, so you have thread here that I'm going to loop a lot while doing some threads, some log-free programming. But what you have to understand is that each operation advances in the right direction, and they only fail if another one had succeed. So they only failed if another thread advanced.
Okay.
And yes, of course, if you do a lot of the operation on this, I mean, yes, if it might happen that you fail a lot, but it's still better to fail a lot than locking and then doing a context switch, which also take a lot of CPU. And yes, there is a trade-off there, but usually it doesn't spin that much.
Okay, and the atomic int class can take any kind of object? I saw that you use a pointer and can refer to pointers which are the Qt objects, or pointer which are...
You can refer to any kind of pointer. So in my case, I was referring to a pointer to a node here. So it's just, so you have QAtomic int that refers to int, and QAtomic pointer which refers to any kind of pointer.
Okay, thank you.
Hi.
Hey.
Yeah. I have two questions. The first one is that I wonder, unless I'm mistaken here, but why we don't have a way to control priority of the threads in the Qt concurrent suite, and it includes run, map, reduce, and all of them. Do you know?
Mm-hmm. There is no way to do that because there is no API to do that. Yeah. And it's true that it would be a good idea to have that in Qt concurrent. But thread priority is really not that useful on desktop application. It's more something like real-time application that uses that. Again, when you use Qt concurrent, yeah, it's true. You might want to control the priority, but the API doesn't allow that.
Yeah. Because even in Qt Creator, for example, the semantic parsing of QML, for example, what we do is that there's a wrapping feature that also inherits from Runnable. It's kind of some hack, because otherwise this would actually blow the CPU and it's just a workaround to control the priority, so we can still use Qt concurrent and benefit from Qt concurrent. But
there is many flow in the Qt concurrent APIs, such as this one, and another one that many people request is to have to control in which thread pool we want to run the stuff, because with Qt concurrent you cannot really choose which thread pool you use. There is only the Qt global thread pool that has to be used basically for CPU intensive operation, but you would also like to have one thread pool for the CPU operations and one other thread pool for some other blocking operation that you have to do in threads, and it's indeed something that is lacking in Qt concurrent.
Okay, and the second question is another curiosity. There's one handy class in the Qt concurrent, which I don't know why it's not documented, which is the Qt future interface. And it's very useful to keep track and control the progress of the future. And it's, at least the last time I checked, I couldn't find any mention of it in the
documentation.
Yeah.
You're supposed to be able to use QFuture and QFuture Watcher to control your futures.
Yeah.
QFuture interface is just there for some internal details. I mean, yeah, of course, there is a lot of internals that customer would like to see exposed.
Yeah, and there's some of them that apparently you can only control through the QFuture interface. Mm-hmm. And we actually have in Qt Creator some extensions that use this Qt future interface for a lot of things because it's very handy. So.
Yes, a lot of feature requests here for Qt concurrent. Then it's the end of DevDays, so have a nice day. Don't forget to provide feedback, please. There's the feedback kiosk there, or you can use it on provide feedback on your mobile application. And yeah, I hope you liked the presentation.